Welcome back. This is video lecture 16.3. We're continuing to talk about waves, and we're continuing to talk about interference of waves. We're going to look at a different outcome of interference. This is chapter 16, section 7, in which we're going to introduce the concepts of standing waves and resonance. But the key idea is that it's still a consequence of interference. It's just a slightly different physical scenario than we studied in section 5. So here's the scenario. We're going to have two sinusoidal waves moving on the same string under tension at the same time, just like we did in section 5. Wave 1 will travel in the plus x direction, just like in section 5. But here's the new wrinkle. Wave 2 is going to travel in the negative x direction. So in other words, I've got two waves traveling on the same medium at the same time, but they're traveling in opposite directions. And I'll talk you through how that can happen physically, but that's the situation. Notice that's different than section 5. In section 5, we had two sinusoidal waves on the same string traveling in the same direction. Now we have two sinusoidal waves on the same string traveling in opposite directions. In fact, that's going to be the only way for now that they're going to differ. Direction of travel. We're going to give them the same amplitude, y max, the same angular wave number, k, and since k equals 2 pi over lambda, the wavelength, they have the same wavelength. Same angular frequency, omega, and since omega equals 2 pi f, they have the same frequency, f. Or omega equals 2 pi over the period, so they have the same period, capital T. And I'm even going to take them to be in phase with each other, phi equal to 0. So what are the two wave functions? Wave 1, y max sine of kx minus omega t. Note the minus sign. This describes a wave traveling in the plus x direction at speed v equal to omega over k. Remember that handy little formula for v? Omega over k. The second wave function, y2, y max sine of kx plus omega t. Note the plus sign. These are the only differences between them, the two waves. A minus sign and a plus sign. The second wave function describes a wave traveling in the negative x direction at speed v equals omega over k. Let's put both those waves on the same stretched string at the same time. What will we observe? That's the net wave. It's the algebraic sum of those two individual waves. Remember, that's called the principle of superposition. Y net equals y1 plus y2, where I'm adding those functions of x and t, y1 plus y2. Here's the line. I factored a y max out front, y max times, square bracket, sine of kx minus omega t plus sine of kx plus omega t. Now, if that's all we wrote for y net, that is not very illuminating. It's correct, but it's not very helpful. But we can use a trig identity to help us be able to identify exactly what kind of a wave we're going to observe. And the trig identity is the same one I used in section 5. The trig identity for what you get when you add two sine functions with their own arguments. Sine alpha plus sine beta. It's the same identity I used in section 5. And I just repeating it here for you. The amazing thing is, I started with adding two sines, and I ended up with multiplying a sine and a cosine. Sine alpha plus sine beta equals 2 times sine of alpha plus beta over 2 times cosine of alpha minus beta over 2. That's what we're going to do, and we're going to let alpha stand for kx plus omega t, and beta will stand for kx minus omega t. Let's see what the trig identity gives. Let's do the alpha, let me get a pen here. Let's do the alpha plus beta over 2. Let's see what we get. Alpha is kx plus omega t plus beta, kx minus omega t. all divided by 2. Looks like I have a plus omega t and a minus omega t, so those cancel. And in the numerator, I have 2 factors of kx. So altogether, I have 2kx over 2. That's just kx. Well, that was simple. All right. Now, what do we get when we do alpha minus beta over 2? See if I can fit this in here. Kx plus omega t for the alpha minus, better do parentheses, kx minus omega t, close parentheses, all over 2. Now I see that it's the factors of kx that cancel. And what I've really got in the numerator is omega t plus omega t. So 2 omega t with 2 in the denominator. Note, of course, that these 2's here and here cancel. So that this is just omega times t. So we're going to put those expressions in. For the alpha plus beta over 2, we're going to put that right there inside the sine. And for the alpha minus beta over 2, we put it right there inside the cosine. Don't forget the 2 out front, and of course the y max that I factored out front. And what's the final expression for the net wave that we will actually observe on the string? What we see is that it is fundamentally different than the function we got in section 5. Now I may have to point out exactly how, but it is fundamentally different. What I got in section 5 for the net wave, remember that was for the 2 sinusoidal waves traveling in the same direction on the string. This is coming from the 2 sinusoidal waves traveling in opposite directions. I got a sine function, and inside that sine function was a kx minus omega t plus phi over 2. Important thing, I had the combination kx minus omega t altogether. Kx minus omega t. That's how I know that in that case I had a traveling wave. Well, you might say, of course you have a traveling wave. You had 2 traveling waves that were there, and you combine them and you get a traveling wave. Okay, but look what happens now in this case. I have sine with a kx for its argument, and a cosine with an omega t. But nowhere do I have a combination like that. Nowhere. That is not present in this wave function for y net. And that's the combination you have to have a traveling wave. So interestingly enough, what I've got out of this now, 2 traveling waves going in opposite directions combined, I don't get a traveling wave. We'll still call it a kind of wave, but we're going to have to give it a different name because it's not a traveling wave. And what everybody calls it, so the resultant is not a traveling wave, everybody calls it a standing wave. Now, until you see it in action, either through an animation or an actual video, you won't understand why it's called that. But I'll show you a video in just a second. And here's what we'll do. We'll take the part that depends on time. Of course, that's this part, cosine omega t. That's the oscillatory part, if you like. That's the wave part. Everything multiplying the time-dependent part will be called the amplitude. So the amplitude of the wave is the absolute value of 2y max sine kx. Okay? But the point is the amplitude now depends on x. So here it is. The amplitude of the net wave is 2y max sine of kx. The amplitude of this standing wave depends on the x value where you are. And different x values will have different amplitudes at that point. And we did not see that in section 5. So there's something quite different going on here. But let's just see for now what are the biggest and the smallest values we can get for the amplitude of this net wave, this so-called standing wave. Well, I look at that formula for the amplitude of the net wave, and it's not hard to deduce what the biggest amplitude will be. It's when the sine kx has its biggest value, and of course the biggest value of sine of anything is 1. So the maximum amplitude that I can get is 2y max. Historically, Any point on the x-axis where we have this maximum amplitude, that point is called an antinode of the wave. That will seem like that comes out of nowhere, but that's what it's called. Now, the whole point, though, is that only certain x values have this maximum amplitude. Only certain x values are at antinodes. Where are those? What are those x values? Well, again, it's not hard. I know when sine equals plus or minus 1. Either one. It's when its argument, in this case kx, is one from among a list of possible values, and I list them here. I put a little subscript an on the x for antinode. K times x, if I'm going to have an antinode, must be one of the numbers from this list. In radians, plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, and the pattern continues. This would be in radians. Okay? Because plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2 are values for which the sine is either plus 1 or minus 1. And therefore, the amplitude will be 2y max, the biggest. Note, what we could do then, let me come down here and write it, is we can tell you the actual x values where the antinodes will be. X antinode. Just divide both sides of that formula I just highlighted by k. Plus or minus pi over 2k, plus or minus 3 pi over 2k, plus or minus 5 pi over 2k, dot, dot, dot. In meters, these are x values, where the antinodes are. Well, those are going to be important points on a standing wave, the points of maximum possible amplitude, the so-called antinodes. We can predict where those will be. All we really have to know is k, the angular wave number. Now, the other extreme are points on the x-axis where I have the minimum amplitude I could get, absolutely smallest. And that minimum amplitude is 0. Where does that occur? Those points are called, by the way, nodes of the standing wave. Those are points on the x-axis that have no amplitude at all. That means those points on the string actually never move. Those points on the string that are at x values, which are nodes, they never move up and down at all because their amplitude is 0. Now, what are those x values? Because those are important for a standing wave. Well, again, it's not a mystery. I need values of k times x such that the sine equals 0. That's this list right here. Kx, and I added an n subscript for node, must be, well, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, plus or minus 4 pi, and on and on and on, in radians. Because the sine of plus or minus pi, plus or minus 2 pi, 3 pi, etc. equals 0. Now I can find the x values of those nodes, the x ends, by dividing both sides of that expression by k. So the locations of the nodes are plus or minus pi over k, plus or minus 2 pi over k, plus or minus 3 pi over k, and on and on and on, in meters. Okay? All right, so let me show you that in action with a Wiley Plus animation. Okay, make sure I've got the one present I want. Okay, so here we go. We're looking now at a Wiley Plus animation. Very similar to the one I showed you in section 5. The top graph, these are all snapshots at time 0 until I run the animation. The top graph is the wave function for wave number 1. That's just a sinusoidal wave with amplitude y max equal to 1 centimeter and wavelength lambda equal to 1 meter. You can tell that by looking at the graph on the top. Okay, and so that wave function would be y max sine of kx minus omega t. It's going to be a wave traveling in the plus x direction. Now the second graph in blue is y2 versus x, snapshot at time 0. And it looks like another sine curve, doesn't it? It's got an amplitude of 1 centimeter and a wavelength of 1 meter. And its wave function is y max sine of kx plus omega t, because that one's going to be traveling in the negative x direction. And then the third graph is y net, what you get when you superpose, add y1 and y2. And whereas you can see when I run the animation that wave 1 is clearly traveling in the plus x direction, and wave 2 is clearly traveling in the negative x direction, look closely at wave 3, and you'll notice it's not traveling at all. I'm going to run it so that you can see what I mean. Ready? Here we go. Look, top curve is going to the right, middle curve is going to the left, bottom curve is going up and down, but neither left nor right. You see why the net wave is called a standing wave? Watch that net wave again. It's not traveling to the left or the right. It's called a standing wave. Okay, let me reset the time to 0. Now there's some important points on the x-axis, namely the points where the amplitude is biggest, antinodes, and the points where the amplitude is smallest, 0, nodes. Okay. Let's figure out where those are to make sure our equations on our slide are correct. Let me go back and forth between this and the slide. All right, here's the first question I'm going to ask. For wave 1 or wave 2, either one, I want us to ask, what's the K value, the angular wave number in radian per meter for 1 or 2? To answer that, you'll need the wavelength. Make sure you can look at the graph 1 and graph 2 and see the wavelength, because now I'm going to go back to my slide. All right, so let me get myself a little bit of room here. And so my first question is, what is the K value for waves 1 and 2? Answer, well, you can calculate it from 2 pi over the wavelength, if you know the wavelength. Do you see what the wavelength was? It was 1 meter. So that's 2 pi radians over 1 meter. That's 2 pi radian per meter. Why am I worried so much about K? Because to find the locations of the antinodes and the nodes, I need to know the K, the angular wave number. So now let's find the locations of these points. Let's do the nodes first. What are the x nodes then for that standing wave? Just go up to that formula for the x node. Let's plug in the K value. The K's downstairs, and the K is 2 pi. So the first node is plus or minus pi over K, which is plus or minus pi over 2 pi meter. But, of course, the pi's cancel, so that's really just plus or minus a half a meter, 0.5 meters. By the way, 0 will work too, won't it? I should put that up there. Also 0, because the sine of 0 is 0. So there's also a node at 0, so let's not forget that one. Let's do another one. Let's see, where's the next one? Plus or minus 2 pi over K. Again, K is 2 pi meter. Well, that's just going to be 1. So plus or minus 1/2 meter, plus or minus 1 meter. The next one will be plus or minus 3/2 meters, i.e. 1.5, and the list goes on. Let's go to the animation and see if that's where the nodes are. 1/2 meter, 1 meter, 1.5 meters, etc. Now you're looking at the bottom. You have to look closely. But you'll see there's tick marks in a scale for the x-axis in meters. And the nodes are the points of zero amplitude, the points that never move up or down. And we can see clearly we've got one at the origin, a node. The next one occurs exactly midway between x equals 0 and x equals 1 meter, so 0.5 meters. The next node occurs at 1 meter. The next node occurs halfway between 1 and 2, so 1.5, and so forth, and it's symmetric on the negative side as well. That got the nodes right. Now let's find where the antinodes are. Let's go back to our notes. Now I want to be able to calculate the location of the antinodes. Now I use the antinode formula up above. The first one is plus or minus pi over 2k, right? So that's 4 pi meters. So the pi's cancel, and that's 0.25, isn't it? Meters. The next one's plus or minus 3 pi over 2k meters. So 3 pi over 4 pi. So 3/4 of a meter, 0.75. And the pattern continues, dot, dot, dot. So let's see if those x values are where the antinodes are, the point of largest amplitude. So the first one should be at 0.25 meters, and that's where I look for a 2 centimeter amplitude, because that's the biggest. The next one is at 0.75 meters, and then 1.25 meters, and so forth. So these formulas do get the correct locations of the nodes and antinodes. And because I started out with just sine kx minus omega t and sine kx plus omega t, I got that net wave with a node at the origin. Let's run it again so you can see that the node points, such as at the origin, never move in the bottom graph. What if I would like to combine two traveling waves, one traveling in plus x, one traveling in negative x, same amplitude, same k, same omega, but I would like to have an antinode at the origin. I wonder how I might do it. Hint, I have another slider here on this animation that lets me control something, namely the phase difference between the two waves, phi. Right now it's set to 0. But what if I adjust it to pi radians? Then, at time 0, at the snapshot, look at the two waves, wave 1 and wave 2. They're exactly out of phase. And now let's run the animation. Reset it. And now the origin is an antinode. I'll let you think a little bit about why that phase difference between the waves produces an antinode. Notice then the formulas I got for the location of the nodes and the antinodes, we need to be clear, that was assuming that the phase difference between the two waves was 0. The only way they differed was in one traveled in plus x and the other traveled in negative x. All right, but we'll have some Wiley Plus practice where we work with standing waves like this. I have one more topic I want to talk about, and we needed to talk about standing waves in general before we could talk about this. We're going to talk now about the resonance of standing waves on a string. And this is the topic of experiment 8 in lab. Okay? And if we had normal situations where you were in the lab for experiment 8, you would be creating what are called standing waves being on a metal wire, not a string, and studying the mathematical properties of those waves. But here, we're going to have to stick to videos and animations and pictures. The idea that the book is imagining is take a horizontal stretched string under tension, drive one end up and down with some kind of a motor usually, although it could be a person with their hand. I do it as a demo in class when I have a classroom. And you create a traveling wave traveling down the string. The other end of that string is usually tied to some rigid support so that that end of the string can't move. You get what's called a reflection off the wave off that fixed end, and you get a wave traveling back. That's how you get a wave traveling in plus x and minus x on the same string. Just let the wave go down. You keep making the wave at one end, let the wave travel down to the other end and have a reflection back, and you're still making wave traveling in the plus x, and now the reflected wave traveling in the negative x, and you got waves traveling in opposite directions at the same time on the same string. Usually that's a jumbled mess, and that the net wave that you observe is complicated and messy. But if you get the frequency that you move up and down your hand or drive the wave just right, you'll get what's called resonance. And you'll get very large standing waves that will be visible for very special frequencies on the string. And that's what we're talking about here. We want to be able to calculate what those frequencies and wavelengths are. We've got some photographs here of a vibrating string that was strobe lit at just the right frequencies. You could see it clearly at 3 different special resonance frequencies of the string. And those are what I want to talk about. What are those resonance frequencies? So now I have some schematic pictures. And the first one shows, again, don't worry about how you drive this. It shows the string fixed at 2 ends. It's got some distance L, so some length L between the 2 ends. And it's showing you what's called the first harmonic resonance. This is the lowest driving frequency that will create a large standing wave on the string. And in this lowest or first harmonic resonance, this lowest frequency resonance, the string just goes up with a peak in the middle, and then half a period later it's down with a trough in the middle, and it just goes up and down, up and down. We'll show you videos and animations. Okay? So that's what this picture shows. In green, it shows a snapshot in time when the string is bowed upward. Notice it has an antinode at the midpoint. And then half a period later with a dashed line, the same string is now downward, making a trough. The wavelength of the full wave, if you could see the full thing, would be from there to there. That'd be one full wavelength. Note that wavelength then is 2L. We're going to call it lambda 1 because it's the wavelength for the first harmonic resonance, and so it's equal to 2L. That means I can also write down a formula for the frequency of that first harmonic resonance, F1. Using one of the standard formulas for a sinusoidal wave, frequency equals speed of wave over wavelength. So F1 equals V, the speed of the waves that are traveling back and forth on the string, over the wavelength lambda 1. Substituting that lambda 1 is 2L, I get the formula for the first harmonic frequency. First harmonic standing wave on this string. F1 is V over 2L. And that's the lowest frequency that you'll get a large amplitude standing wave on that string. V over 2L. Notice the 2 things that determine that lowest frequency. V, how fast do the waves travel on the string? Remember, we already know the formula for that. And that's the square root of the tension in the string over the mass per unit length. So we control what that V is by controlling the tension of the string and its mass per unit length. V over 2L is the lowest frequency standing wave we can see. It's called the first harmonic. And if you're a musician, you probably have heard that phrase. What's the next highest frequency standing wave that will give you a big amplitude? It's called the second harmonic resonance. And it's one in which you fit exactly one wavelength over the distance L. So there it is at one snapshot in time. I just drew it in green. Half a period later, I'll draw with a dashed green curve. It'll be just the reverse, like that. And that's the second harmonic. So the wavelength for that, lambda 2, notice how I'm going to write it. 2L over 2, because that's true, L. And the frequency F2 is V over lambda 2. But plug in the lambda 2, 2L over 2, but write it like that. 2 times V over 2L. But V over 2L was F1, the frequency of the first harmonic. So the frequency of the second harmonic is just twice the frequency of the first harmonic. That's a nice little pattern, isn't it? So that second harmonic will oscillate at twice the frequency of the first and half the wavelength. Let's do one more. What's the next highest frequency that will give you a standing wave resonance on the string? It's called the third harmonic resonance. And in that one, you can fit 1.5 wavelengths over the distance L. And half a period later, the picture looks like the dashed line. So the wavelength lambda 3 of the third harmonic is 2L over 3. And the corresponding frequency of the third harmonic, F3, is V over lambda 3. But for lambda 3, substitute 2L over 3 and write it like this: 3 times V over 2L, or 3 times F1. So we're starting to see a pattern here, yes? Let's write down the general result for what is called the nth harmonic, because this goes on forever, technically. The wavelength of the nth harmonic, lambda sub n, is 2L over n. As you go up in integer steps with n, the wavelength gets smaller. But the frequency of the nth harmonic, f sub n, which is v over lambda n, is n times v over 2L. It's n times f1. So the frequencies go up as integer multiples of f1. And these are very handy little formulas. And musicians who play stringed instruments in particular learn a lot in very theory into practice way about creating harmonics in vibrating strings. All right. Let me show you a couple of things now. First, in Wiley Plus, let me show you an actual video. This is what I would do in class if we were in a classroom, where somebody took a string, put it under a certain amount of tension, fixed one end, and drove the other end, in this case with an electric drill, and could adjust the frequency at which they drive it. Standing waves on a string. I'll turn off his video, his audio. He's just explaining the setup there, but you can see the long string. You can see the weights at the other end giving him his tension. But the other end where the pulley is prevents that end of the string from vibrating. And then he's got just an electric drill at the other end, and he can control the rate at which it spins with an object there called a variac. So he's just going to change the frequency of that drill, and therefore he's changing the driving frequency of the wave. He's going to look for these standing wave resonances, these harmonics. Here he goes. See, he just causes that thing to turn. And he's first going to find the first harmonic. There it is, with a large antinode in the middle. Now he's doubling the frequency, and he gets the second harmonic with a node in the middle. And now he's going to try to get the third harmonic. It's tricky to find them sometimes. He doesn't do the greatest job finding the third harmonic there. He's pretty close. Now it keeps increasing the frequency. He's going to try to find the fourth harmonic. Doesn't do the best job finding it. It's roughly there. Then he's going to try to find the fifth harmonic. Does a little bit better job finding that. There. Actually, what he's got there is the fourth. He was struggling to find it, but he's found the fourth. So he's finding the first, the second, the third, the fourth. They can be hard to find a lot, too many. But I just wanted you to see that with a real string, under real conditions, you can make these standing waves. I don't want you to think that it's something we're making up. But now let me show you another animation where we represent a string, horizontal string. It's got a length of 1 meter. It's that brown line along the x-axis on the graph there. And when I run the animation, we're going to drive it at a frequency F1 of 130 Hertz, which for the tension in that string happens to be the first harmonic resonance frequency. But we're going to run this at a exaggerated time scale so that you can see it going up and down. First harmonic resonance. Down and up. With an antinode at the midpoint. Okay? An antinode at the midpoint. And it's just going up and down at a frequency of 130 Hertz. Just change the time scale so that you can see it. All right, now with the harmonic index n, I can go up 1 to n equals 2. And now we're going to drive at the frequency for the second harmonic. And if the first harmonic frequency was at 130 Hertz, what's going to be this frequency? 260? Twice what the F1 was. And look what you get now. You get a second harmonic resonant wave at frequency F2. It's clearly oscillating up and down more rapidly than F1, than the first one. And there's a node in the middle and 2 antinodes on either side of that middle. Notice 1 node in the middle with the second harmonic. Now let's go to the third. And we're going to drive it now at a frequency of F3, which is 3 times F1. Let's see what we see. 2 nodes. One at 1/3 of L and the other at 2/3 of L. And 3 antinodes. And faster oscillation, more rapid oscillation. How about the fourth harmonic? All right, now at F4, we're going even more rapid oscillation. 3 nodes in the middle region, 4 antinodes. N equals 5, F5. 4 nodes in the middle region, 5 antinodes. N equals 6, F6. 5 nodes, 6 antinodes, and very rapid oscillation. And finally, we can get up to 7. There would be more in principle, but we just can only see 7 on this animation. 6 nodes, 7 antinodes, very rapid oscillation. Okay, so those are standing waves on a stretched string. And that is the physics underlying, pretty much, all of the behavior of stringed musical instruments. So what we're going to leave with today, and our class on Monday will be practicing with standing waves, is a little class engagement exercise on Blackboard. For Monday. Just a couple of questions for practice that go like this. If you set up the 7th harmonic on a string, as I showed you on the animation, questions. How many nodes are present, not counting the nodes at the 2 ends? How many? Is there a node, an antinode, or some intermediate state at the very middle point of the string? Next, suppose you set up the 6th harmonic. So that was the 7th harmonic. Now the 6th harmonic. Is the 6th harmonic, resonant wavelength longer or shorter than that for the 7th harmonic? And is its resonant frequency higher or lower than that for the seventh harmonic? You just enter those 4 answers into Blackboard as some practice on the properties of standing waves, and then we'll talk more about standing waves in our Monday class. That's all for this video.